The story began in 2017, more than 12 billion miles from Earth, where a spacecraft that had already outlived every expectation quietly stumbled across something no one had imagined it would ever find. Voyager 1 had been traveling through the darkness for 4 decades. By then, it was an aging machine, built with 1970s technology and powered by a steadily weakening nuclear battery. Most people assumed its greatest discoveries belonged to the distant past, to the spectacular flybys of Jupiter and Saturn that had made it famous. Yet, far beyond the worlds it had once photographed, the old spacecraft was about to reveal something even more surprising. But before we uncover what Voyager 1 found, take a second to subscribe to the channel. We're getting closer to our goal of 1,000 subscribers. One of its remaining scientific instruments began detecting a signal. It wasn't dramatic. There was no sudden burst of energy, no violent spike that demanded immediate attention. Instead, it appeared as something far stranger, a faint, narrow signal that refused to disappear. The scientists monitoring Voyager 1's data expected it to fade away after a few days, just as every previous plasma disturbance in interstellar space eventually had. But this one didn't. Days became weeks. Weeks became months. Months became years. The signal remained. That simple fact immediately created a problem. NASA had sent Voyager 1 beyond Jupiter, beyond Saturn, beyond the very edge of the solar system, into the enormous gulf between the stars. For decades, physicists had developed sophisticated models describing what that region of space should be like. Every calculation, every simulation, and every peer-reviewed theory painted roughly the same picture. None of them predicted what Voyager 1 was now quietly reporting. Years later, Stella Koch-Ocker, the Cornell University researcher who led the team investigating the mysterious signal, would explain just how unexpected the discovery really was. Before Voyager reached interstellar space, scientists imagined the region as something like a gentle rainfall. There would be a steady but quiet background, occasionally interrupted by larger disturbances, much like distant flashes of lightning during a storm. Those temporary bursts made sense because they could be traced back to powerful eruptions from the Sun, whose shock waves traveled outward for months or even years before finally reaching interstellar space. Everything fit the models, until Voyager listened more carefully. Instead of silence between those occasional bursts, the spacecraft kept hearing something else entirely. A constant, quiet hum. It wasn't loud, it wasn't dramatic, but it was always there. The discovery immediately raised an uncomfortable question. If this background signal truly existed, why had nobody predicted it? The answer was surprisingly simple. Until Voyager 1 crossed into interstellar space, nobody had ever placed a scientific instrument there. Every previous model had been built from the safety of Earth's neighborhood, using telescopes, mathematics, and theoretical physics. Scientists had been studying the space between the stars entirely from the inside of the Sun's protective bubble. Voyager 1 changed that. For the first time in history, humanity wasn't simply observing interstellar space. It was inside it. Understanding why that mattered required looking back to the beginning of Voyager's extraordinary journey. When Voyager 1 lifted off on September 5, 1977, nobody imagined it would still be working nearly half a century later. The mission itself had been designed to last only 5 years. Its objective was straightforward: fly past Jupiter, continue to Saturn, collect as much scientific information as possible, and eventually fall silent forever. Instead, the giant planets did something remarkable. Their immense gravity accelerated Voyager like a perfectly aimed slingshot, throwing the spacecraft farther and farther from the Sun with every encounter. Decade after decade, it continued its lonely journey into deeper space. Then, on August 25, 2012, Voyager reached one of the most significant milestones in the history of exploration. It crossed the heliopause. This invisible boundary marks the point where the solar wind, the constant stream of charged particles flowing outward from the Sun, can no longer push back against the pressure of the interstellar medium surrounding our solar system. Beyond that boundary lies true interstellar space. When Voyager crossed it, humanity became an interstellar species for the very first time. Unlike every telescope on Earth, which still observes the universe from within the Sun's protective bubble, Voyager was physically present in the environment scientists had spent generations trying to understand, and it never stopped sending information home. Even today, it remains the only continuously operating scientific instrument ever placed directly inside the space between the stars. Long before that historic crossing, researchers had invested decades developing increasingly sophisticated theories describing the interstellar medium. These were not educated guesses or speculative ideas. They were built from rigorous plasma physics, detailed mathematical modeling, and countless peer-reviewed studies examining how charged particles behave in incredibly thin, cold environments. Remarkably, almost every model reached the same conclusion. Interstellar space should be relatively calm. Its plasma should be extremely sparse, with particles drifting quietly through space. Most of the time, very little should happen. Only occasionally would a powerful shock wave from a major solar eruption travel outward across billions of miles before disturbing that otherwise peaceful environment. Between those rare events, scientists expected almost complete silence. Voyager 1 carried a plasma wave instrument specifically designed to detect tiny oscillations within surrounding plasma. It could measure the faint electromagnetic signatures produced whenever charged particles interacted with one another. For the first several years after crossing the heliopause, the instrument behaved exactly as expected. It detected the occasional plasma disturbances created by known solar shock waves. Then everything returned to silence, or so everyone believed. Only later did researchers realize that the silence had never truly existed. Hidden beneath those temporary bursts was a faint but persistent hum that had been present all along, quietly waiting for humanity's first interstellar explorer to notice it. For years, everything unfolded exactly as scientists had predicted. Beyond the occasional disturbance caused by a powerful shock wave racing outward from the Sun, interstellar space appeared almost perfectly still. Between those rare events, researchers expected silence, or at least something so faint that it would never register as meaningful data. Voyager 1 was equipped to test that assumption. Among the few scientific instruments that had survived decades of operation was its plasma wave instrument, a remarkably sensitive device designed to detect tiny oscillations within the surrounding plasma. Every time charged particles vibrated or interacted with one another, they produced faint electromagnetic signatures. The instrument could hear those signatures, allowing scientists on Earth to study an environment no human-made object had ever explored directly. When Voyager crossed the heliopause in 2012, the instrument behaved exactly as expected. Whenever a shock wave generated by an eruption on the Sun eventually reached interstellar space, the instrument recorded it. Once the disturbance passed, everything returned to what appeared to be quiet. For several years, nothing seemed unusual. Then, in 2017, the story changed. As researchers continued examining the incoming data, they noticed something that refused to fit any existing explanation. Hidden beneath the expected signals was a faint but unmistakable emission. It wasn't a temporary burst. It wasn't linked to any known solar eruption. Instead, it appeared as a narrow, persistent band that remained present day after day, week after week, and year after year. Rather than fading into silence, the signal simply continued humming quietly in the background. The discovery immediately attracted the attention of Stella Koch-Ocker and her colleagues at Cornell University. As they carefully analyzed years of Voyager 1's observations, they realized they were looking at something entirely unexpected. Later, when describing the discovery, Koch-Ocker offered a comparison that perfectly captured how dramatically scientists' understanding had changed. Before Voyager's observations, researchers had imagined interstellar space behaving much like a gentle rainfall. Most of the time, there would be a soft, even background, interrupted only occasionally by larger disturbances, like distant flashes of lightning during a storm. Voyager revealed a completely different picture. Once the team looked closely between those familiar bursts, they discovered that the quiet moments had never been truly quiet at all. Beneath everything was a constant, low murmur. It had always been there. The reason nobody had predicted it was surprisingly simple. Until Voyager 1 entered interstellar space, no scientific instrument had ever remained there continuously, with enough sensitivity and enough time to detect such a subtle background signal. Humanity simply had never listened closely enough. Nor was the discovery some tiny statistical curiosity. As Voyager continued traveling farther into the darkness, the persistent emission remained detectable across more than 900 million miles of its journey, roughly 10 times the distance separating Earth from the Sun. The consistency of the signal convinced researchers that they were observing something physically real. It was not random interference. It was not electronic noise. Instead, it appeared to be revealing a genuine property of interstellar plasma itself. When the team's findings were published in the peer-reviewed journal Nature Astronomy, their conclusion was strikingly direct. Interstellar space, they wrote, was not the quiet, uniform void that decades of theoretical models had described. It was turbulent. It possessed genuine physical structure across every scale they could measure, from distances measured in meters to structures stretching across millions of miles. For the first time, scientists could say that the space between the stars was far more dynamic than anyone had realized. It was filled with constant motion and hidden complexity that had remained invisible simply because no one had ever measured it directly before. That realization forced researchers to pause. For generations, every model of interstellar space had been created from the outside looking in. Astronomers had relied on telescopes, mathematical calculations, and theoretical physics, all while remaining safely inside the protective boundary of the solar system. Voyager 1 changed that completely. For the first time, humanity had an instrument living inside the environment itself. And what it reported suggested that those carefully constructed models were missing something fundamental. The universe beyond the Sun's protective bubble appeared richer, more dynamic, and considerably more complex than scientists had imagined. The importance of that discovery extended far beyond academic curiosity. The heliopause is not merely an invisible boundary separating the solar system from interstellar space. It acts as a protective shield. As our solar system travels through the galaxy, this boundary helps deflect a significant portion of the dangerous cosmic radiation constantly streaming toward us from distant stellar explosions. Without that protection, far more high-energy particles would penetrate the inner solar system, reaching Earth with greater intensity. That raised an obvious question. If the interstellar environment pressing against the heliopause is far more turbulent, energetic, and variable than scientists had believed, could the behavior of that protective shield also be more complicated than anyone had realized? At present, nobody knows the answer. researchers have been careful not to overstate what Voyager's discovery means for Earth itself. There is still too much uncertainty to draw firm conclusions. Yet the discovery changed something important. Questions that once existed only as theoretical possibilities could now be investigated using real measurements gathered from interstellar space itself. In that sense alone, Voyager had already transformed our understanding of how the solar system interacts with the wider galaxy. Even so, one crucial mystery remained unresolved. And perhaps that uncertainty is the most fascinating part of the entire story. After years of analysis, researchers concluded that two competing physical explanations could account for the persistent signal. The first possibility was relatively familiar. The emission might simply be produced by thermally excited plasma oscillations, the natural vibrations created as charged particles constantly interact with their immediate surroundings. If that explanation proved correct, the discovery would still be enormously important. It would reveal a previously undetected feature of interstellar space, while fitting comfortably within the established framework of plasma physics. It would expand existing theory, but it would not fundamentally change it. But there was another possibility. It was more complicated, more intriguing, and potentially far more significant. Researchers realized that the mysterious signal might not be produced by ordinary plasma oscillations at all. Instead, it could be the result of a phenomenon known as quasi-thermal noise. Although closely related to the first explanation, it represents a meaningfully different physical process, one capable of revealing the density and temperature of interstellar plasma in a subtly yet fundamentally different way. If that explanation eventually proves correct, the consequences would extend far beyond the discovery of a new signal. It would mean that scientists would have to substantially revise their existing models of the interstellar medium rather than simply improve them. At the moment, however, nobody knows which explanation is right. To settle the question, researchers need one of two things. They either need many more years of measurements from Voyager 1 itself, or they need an entirely new spacecraft designed specifically to explore interstellar space, with instruments built for exactly this kind of investigation. And that is where the story suddenly becomes urgent. Neither of those possibilities is guaranteed. Every year, Voyager 1 grows a little weaker. The spacecraft generates its electricity through the slow radioactive decay of plutonium inside 3 aging thermoelectric generators. That power supply steadily decreases by roughly 4 watts every year, and every watt that disappears is gone forever. No one can refuel the spacecraft. No one can repair it. Its long journey has become a race against time. When Voyager 1 launched in 1977, it carried 10 scientific instruments. Today, after nearly 5 decades in space, only 2 of them are still operating. Keeping those remaining instruments alive has become an extraordinary engineering challenge. Year after year, NASA engineers have been forced to decide which systems can remain switched on and which must be permanently shut down, sacrificing one capability after another simply to preserve the mission for a little longer. At the same time, there is no successor waiting to continue Voyager's work. No dedicated mission built to travel into interstellar space and make these measurements has been approved, and none is currently funded. Even if a replacement spacecraft were authorized today, fully funded and launched immediately, current estimates suggest it would need at least 25 years just to reach the heliopause, the same invisible boundary that Voyager 1 crossed back in 2012. That reality gives the mystery an entirely different perspective. The question at the heart of Voyager's discovery, whether the persistent hum comes from ordinary thermal plasma oscillations or from quasi-thermal noise requiring a genuine revision of existing physics, may remain unanswered long after Voyager itself has fallen silent. Engineers expect that moment to arrive sometime during the early 2030s. Eventually, the spacecraft's remaining power will no longer be enough to operate even its final instruments. When that day comes, humanity will lose something it has possessed for only a brief moment in history. The only continuous, real-time scientific observer ever placed inside interstellar space will stop speaking forever. Yet the question it uncovered will remain, quietly waiting, perhaps for decades. Looking back over the entire story, the facts themselves are remarkable enough that they need no exaggeration. A spacecraft built with 1970s technology, originally expected to survive only 5 years, is now nearly half a century old. Powered by less electricity than a typical household light bulb, and traveling more than 15 billion miles from the engineers who still communicate with it, Voyager 1 has quietly detected a persistent signal that no scientific model predicted should exist. Scientists have confirmed that the signal is genuine. They have observed it consistently across hundreds of millions of miles as Voyager has continued its lonely journey through interstellar space. And despite years of careful analysis, they still cannot say with complete confidence exactly what is producing it, or what it ultimately reveals about the relationship between the wider galaxy and the fragile protective bubble surrounding our solar system, the bubble that has sheltered every human being who has ever lived.